Hello, welcome. In this video we are going to discuss chapter 5 of Principles of Topology by Friedrich Kroon. We are going to see the definition of connectedness and disconnectedness which are defined on topological spaces. But see, the connectedness is a property of topological spaces, but that can be explained in connection with real objects. For example, you can see two pencils in this figure. See, this pencil is connected, and the other one, it's a broken pencil. The second pencil is a broken one, so we say that it is a disconnected pencil. But how can we explain that this pencil is disconnected? For that, see, it's a kind of mathematical way of explaining that disconnectedness. See, for that we name this part. See, you can see here this pencil has two sections, and so the first section can be named A, and the second section can be named B. To make sure that, or to say that the first section is existing, or it is not empty, we shall ensure, or we shall write A is not a null set, so or A is non-empty. That means A exists, and similarly to say that the second one also exists, so B is not empty. So first condition that must be satisfied by A and B are A is non-empty and B is non-empty. And we also know that when you take the two sections together, we get the whole thing, the whole pencil. So you can write A union B equal to the whole pencil. A union B equal to the whole thing. But if we call the whole thing X, then you can write that X is equal to A union B. Moreover, since there is no common point, or there is no point shared by the two sections A and B, that means A intersection B, there is no common point, that means A intersection B is a null set. So this can be used, and this type of explanation, this kind of explanation can be used to define the disconnectedness of a topological space. See, the notion of connectedness, it is associated with that is associated with the topological space, can be explained using some examples. So we use some examples to explain that concept a little more. See, for that we consider, let us take the real line, or we take X is equal to R, the real line. It's a topological space, and we know that there is no gap between any 2 points on R. See, on the real line, see that we know that points are packed continuously. They are arranged on the real line. There is no gap between any 2 points, or there are no points are missing from the real line. So see, that's illustrated here. See the figure. In this figure, we have a real line. And we take 2 points A and B on this line. And you know that no point is missing from this real line. But another topological space, that's a subspace of we consider another topological space Y. It's a subspace of the real line, that is illustrated, that is given here in the second figure. Y equal to AB, the interval AB union CD, the union of two intervals AB union CD. here given it's drawn here using this green color AB, the open interval AB, and this is the open interval CD. But you know, since it's the union of two separated open intervals, see the points between B and C are not there in the subspace. Y is the subspace here, so we have to say that that subspace is not connected, it's disconnected. So thus we have two examples of spaces. One is the first one is connected, the x is equal to real line is connected, but its subspace y equal to the union of open interval AB and CD is disconnected. Okay, and again one more example let's consider that will illustrate connectedness and disconnectedness in topological space. We consider x is equal to R2, the Euclidean two-dimensional space R2, x equal to R2 equal to R cross R, and y equal to R. It's a subspace of it's a subset of that topological space. It's a subspace also. That subspace can be removed. We are removing that subspace from the whole space R2, and that is that we define thus we define Z equal to x minus y. That's R2 minus R. And then it's a disconnected space. Why it's a disconnected space? It's because this is the entire space R2, that's R cross R, and we remove the real line. We remove the real line from R2, and thus we get the upper half and the lower half. That's they are separated. Upper half of the plane, upper half plane is separated from the lower half plane by using this line, the real line. So we get the union of two subspace. See, Z equal to the space Z equal to x minus y. It's is the union of two half planes, and that are not actually connected. So we have to say that that subspace is disconnected. Now we can define the disconnected spaces, and then we will define connected spaces. So can we define a disconnected space? A topological space X is said to be disconnected or separated. We say that a topological space is disconnected or separated if it can be expressed as the union of two disjoint non-empty open sets. See, if it can be expressed as, if the topological space can be expressed as the union of two disjoint non-empty open sets, then that means there exists two open sets A and B such that X is equal to the whole space equal to the union of the two open sets A union B. X equal to A union B. X is empty set also. Moreover, we have the conditions. The first set A is an empty set, and B, the second set, is an empty set. It's not an empty set. See, that first and second subsets, so all the open sets A and B are not empty sets. B is also it's not an empty set, and their intersection but must be empty. That means there is no common point for the open sets A and B. So A intersection B is an empty set. And the pair A and B, in this situation, A and the pair is the pair A and B is called a separation of X. The pair of open sets A and B is called a separation of X. A topological space X is connected. And now we can define connectedness of a topological space. A topological space X is connected if it is not disconnected. So if a topological space cannot be disconnected, if it is not a disconnected space, then we say that it is a connected space. So x equal to r, the space x equal to r is connected, but the subspace y equal to minus infinity 0, that's the union of two open intervals, minus infinity 0 union 0 plus infinity, is disconnected. There is a see, it's because there is a point missing, the point 0 is missing from the real line, and that makes this the subspace y. Y is obtained by removing the point 0 from the real line, so the subspace y is disconnected. See, now we discuss two problems on connectedness or disconnectedness of the real line, actually, or it's a real line and subset of the real line. It's a closed interval. In the second problem we will discuss the connectedness of a closed interval, that's a subset of the real line. So first we see that the real line R with the usual topology is connected. We want to show that R is connected with the usual topology. And we suppose that R is disconnected. Now to show that it is connected, let's suppose that it is disconnected, and then if it is disconnected, there exists two open sets A and B, such that it makes the disconnection of the topological space R, that's x equal to R equal to A union B, and A is non-empty and B is non-empty, and A intersection B is empty. Clearly, if we can write A equal to R minus B, or it is the complement. A is the complement of B. So A equal to R minus B is the complement of B. So it's since B is open, and then it's clear that A is closed. Since B is open and R is the whole space, so A must be closed. And also we can the other way also we can say, that is B is equal, since B equal to R minus A, that's equal to complement of A, and this is not closure of A, it's equal to complement of A complement, and so B is also closed. Thus the subsets or the open sets A and B are closed also simultaneously. Next we consider 2 points. One point from A and another point from B. That's A belongs to A. The point A belongs to A and B belongs to B. Now, without loss of generality, we can assume that A less than B. And so suppose A is greater than B, then by relabeling them or renaming them, we can make that A less than B. So that's not a problem. So which one is greater is not a problem. It just by interchanging the role of A and B, we can make that the first one is or one is less than the other. Then we define A prime. We define A prime, that's equal to A intersection the closed interval A intersection the closed interval AB. So we define A prime in the new set A prime equal to A intersection closed interval AB, but A prime is closed by because A is closed and AB the closed interval AB is also closed, so their intersection is closed. Thus A prime is closed and also it is bounded. A prime is closed and bounded because AB is bounded. The interval AB is bounded, hence its intersection with that set is also bounded. Thus it is closed and bounded. It's a closed and bounded subset of R. So it contains its least upper bound C. Say C is the least upper bound, and then it is contained in A prime. But C cannot be equal to B. What happens if C equal to B? See, in this situation here, C cannot be equal to B. Why? Because C is an element of A. We know that C is an element of A, but B is an element of B. B an element of B. But if C is equal to B, what happens? Then C becomes an element of B also. So C is an element of A and C is an element of B. That implies that there exists a common point for A and B, and then it contradicts the fact or the condition that we have accepted on A and B, that is A intersection B equal to empty set, and that is contradicted by this situation. If the point C and B are equal, if C equal to B, then we get a contradiction. So we have to take that C less than B. So C is less than B. Also, see A intersection C, the open closed interval CB. A intersection the open closed interval CB equal to the null set. Why? It's because A intersection CB, the open here CB is the open closed interval. CB is a null set. And hence it's because C is the least upper bound of C access the least upper bound for the set A intersection AB. Okay, thus it is clear that C and the point C and the remaining points or the points, any point which is greater than C cannot be a part of A, and that is A intersection CB, A intersection the open closed interval CB equal to the null set. Therefore it must be a part of B, because A and B, the union of A and B equal to R. So CB, the open closed interval CB, is a subset of B, and we know that C is a limit point of that interval, the open closed interval. C is a limit point of this open closed interval CB. Since B is closed, then C must belong to B, and thus we get that C belongs to B. Thus finally we get that C belongs to B and C belongs to A, and this contradicts the accepted statement that A intersection B equal to a null set. A intersection B equal to null set is contradicted by by the statement that C belongs to B and already C belongs to A. And thus we get finally the contradiction. Therefore the real line R cannot be it cannot be a disconnected set, a disconnected space. And the next problem here, we want to show that every closed interval is connected. Every closed subinterval of the real line is connected. See, we can show that the closed interval is the connectedness of closed interval can be proved using the same steps, or by recreating the all the steps by using the substitution that R by using the substitution of R by the closed interval PQ. See, for that we consider we take the closed interval PQ to write the proof of the problem. We consider the closed interval PQ, and what we do then, we consider we take all the steps in the previous problem, steps of the proof in the previous problem, and we replace all R by the closed interval PQ. So just by replacing R by PQ, we can obtain the proof easily for this problem. Okay, and that's the way of writing the proof of the problem. Next we shall show that the connectedness is a topological property. We have a theorem in which we want to show that connectedness is a topological property. See, for that we want to show that when X and Y are topologically equivalent, when we have two spaces, suppose we have two spaces X and Y, and when they are topologically equivalent, then X is that is X is connected. When they are topologically equivalent, X is connected if and only if Y is connected. See, when we consider two spaces X and Y, they are topologically equivalent spaces, then X is connected if and only if Y is connected, or X is disconnected if and only if Y is disconnected. That's the other way of doing this. X is disconnected if and only if y is disconnected. See, since x and y are topologically equivalent, there exists a homeomorphism. There exists a homeomorphism, say f. F is the homeomorphism that exists from x to y, that can be defined from x to y. And we know that f is 1 to 1. Then when it is a homeomorphism, when f is a homeomorphism, then f is 1 to 1 and on to. Also, both f and f inverse are continuous. Thus, see, since f is a homeomorphism, f is 1 to 1 and on to, and also f and f inverse are continuous. And suppose that x is disconnected. Now we suppose that x is disconnected. Then there exists. Based on this supposition, we want to show that y is also then disconnected. So whenever x is disconnected, we want to show that y is disconnected. But when x is disconnected, we know that there exists a disconnection for x. Then there exists two open sets A and B, such that x equal to A union B. A is an empty set. A is not an empty set. A is not empty, and B is also not empty. But their intersection, A intersection B is an empty set. Now let's consider the homeomorphism from x to y. We then substitute f is defined from x to y. Well, we also know that f of x is equal to, that is the complete image of the space, the image of the complete space. See, the image of the complete space under the function f, that is f of x, but x is equal to A union B, and therefore f of A union B, we can write f of A union B, f of x equal to f of A union B, but it's equal to fa union fb. F of A union B equal to fa union fb. Why? It's because f is 1 to 1 and on to. The property of property that f is 1 to 1 and on to says that f of A union B can be expanded as f of A union f of b, and since f inverse is continuous, since f inverse is continuous and both fa and fb are open, using the continuity of f inverse, since f inverse is continuous, we know that fa and fb are open. Why? It's because A is open, A and B are open in X, therefore f of A and f of B are open. And A is not equal to the null set. A is a non-empty set, and that implies therefore f of A is also a non-empty set, and B is not not an empty set, or B is a non-empty set. Implies that, see, this is you have to write here you have to correct it, the empty set actually. It's the symbol, it should be corrected to empty set, it's not 0. So B is a non-empty set. That implies that f of B is also non-empty. F of B is also non-empty. Thus we get f of A non-empty, f of B is also non-empty, and f of A and f of B are open sets, are open subsets of Y, and therefore and one more thing, see, when we take the intersection f of A intersection f of B, that's an empty set. It's because of the one-to-one nature of the function. Since the function f is 1 to 1, see, you can easily verify that f of A intersection f of B is an empty set. Thus, thus we get that f of A and f of B make a disconnection for the topological space Y. See, but this can be explained furthermore. F of A intersection f of B equal to phi. To explain it more, let's assume that there exists an element in their intersection. See, let x be an element of f A intersection f of B, and then there exists a in a point A in the first open set in A, such that f of A equal to x, and there exists B in B such that f of B equal to x. And this is a contradiction to the fact that thus there exists 2 points A and B such that their images are same. So f of A equal to x and f of B equal to x. What does it mean? It means that the point A, is mapped to X, at the same time the point B is mapped to X. So that's actually a contradiction to the fact that F is 1 to 1. So since F is 1 to 1, we get that F of A intersection F of B equal to the empty set. And thus it is now clear that the subsets of Y, that's F of A and F of B, are two subsets of Y, and they satisfy all the requirements of a disconnection. Thus we can say that F of A and F of B make a disconnection for the space F of Y. Hence, whenever X is disconnected, we get that F of X is disconnected. Thus we get this, and we get this using the fact that F is a homeomorphism, and that X has a disconnection actually. We next suppose that X is then connected. Next we want to show that when X is connected, then Y is and Y is also then connected. Next we suppose that X is connected, and we just then assume suppose that Y is disconnected. So while X being connected, we assume that Y is disconnected. Now we will verify whether this situation is possible. We can show that this situation is impossible, it is not possible. So for that, let's proceed by choosing C and D be two open sets which make a disconnection for Y. So let C and D be two open sets that make the disconnection for Y. It's because we have just assumed that Y is disconnected. We have supposed that we have just assumed that Y is disconnected. We have supposed that X is connected, and at the same time we have assumed that Y is disconnected, and then naturally we can choose two open sets C and D, two open sets such that Y is equal to C union D, and C is not equal to the empty set, and D is not equal to the empty set, and C intersection D is equal to, but C intersection D is the empty set. Since F is continuous, but at the same time there exists the homeomorphism F, and since F is continuous, and if F in ways of F is continuous, then you can think about F in ways of C and F in ways of D. Since F is continuous, then F in ways of C, since C is open, and therefore F in ways of C is open in okay, and since it is since F is continuous, then it's F in ways of C. F in ways of C and F in ways of D are open in X. Okay, using the continuity property of F, and then and also we know that C and D are open sets in Y. Since C and D are open sets in Y, then F in ways of C and F in ways of D are open sets in X, and thus we get that we get easily a disconnection for X. We can show that F in ways of C and F in ways of D that really make a disconnection. It make a disconnection for X. That is X is equal to F in ways of C union F in ways of D, and F in ways of C is non-empty, F in ways of D is non-empty, and their intersection is empty. And this contradicts the assumption that X is connected, but actually we get the contradiction. So if there exists a disconnection for X, that contradicts the supposition that X is connected. Okay. Thus we have reached the end of the proof of the fact that topological property, the topological property, their connectedness is a topological property. So the proof of the topological property that that connectedness of two connectedness is a topological property is now complete. Okay, thank you.